Yeah, welcome everyone. This week we have great pleasure to have William Graham to tell us about equivariant cohomology.
Okay, so well, thank you very much. So I'll just write that on here. And so I know that many of you in the audience are very knowledgeable about this topic. So my apologies, this talk is not really for you, but not that of course you're very welcome to be here. So, but anyway, I mean, maybe as motivation, I could just say, if suppose that G, which we can sort of think of it as, in this talk, it will always be like connected linear algebraic group. Although this doesn't, of course, this doesn't matter at this point. X on X, for in this talk, it will be like a complex algebraic variety. And you want to study the space of orbits, which is X mod G. Well, the problem is that even if X is nice, X mod G might not be very nice at all. So even and so I guess this was Borel who had the idea, at least this appears in this Borel's work. Probably he talked about this at IAS, in the 1950s. So we're kind of revisiting. Is that we want to replace X by EG cross X, where EG is a contractible space GX freely, so there's no stabilizers. And I have a nice principal bundle quotient EG going to EG mod G, which is BG, which is called the classifying space. And then because EG is contractible, this space would have the same homotopy type as X. So you're not changing it, but you're making the action better. And so then GX on EG cross X. And I'm gonna think of this as an action on the right on EG and on the left on G. So I can always go back and forth between left and right actions by putting in an inverse appropriately. So I'm not gonna worry about that too much. But I'm gonna have it act on the right here by EG G inverse of X. This is called the mixing action. And then the quotient EG cross X mod G, I will denote by EG cross upper G of X. This is sometimes called a mixed space. I'll denote this by X lower G. And then by definition, the ith equivariant cohomology group of X is equal to the ith cohomology group of XG. And at some point I'll switch to rational coefficients. It's not really necessary now, but for certain things, it might be. Okay. Now, there's some caveats one might make here. So first of all, so just to say, unfortunately, EG is not a finite dimensional space. So we want to go into the say in the land of algebraic varieties. That's not so good. Not finite dimensional. But we can find a finite dimensional. We'll see this in a few minutes. Find a finite dimensional. I'll call it EGM, going to the quotient, which I'll call BGM, such that I can't require this to be contractible, but this is again a principal bundle, assumed to be a principal bundle. So it's a free action. Such that the reduced homology of e.g. M is 0 for I less than or equal to M. And then I can define HIG of X to be HI of EGM cross upper G of X, as long as I is less than M. And then this, of course, one needs to check that this is independent of the particular M and maybe even of the particular choice of EG. So I'm actually not going to check that any of these things are independent of the choices. Fortunately, we have several very nice references for this topic, including a book that recently appeared. So, but it's not too hard to check. But anyway, I'm not going to do that. It doesn't depend on the choice of M. So in fact, I'm not going to make too much. I'm not going to be too precise about M. The idea is I can just make M as large as I want, as large as need to be, as long as it's big enough for any M. So I'm not going to worry too much about the index. Okay, so I'm going to compute some simple examples, but it's actually helpful to say a few facts before computing any examples. So just a couple of facts. So the first one is that H star of G of X, or just H star of G, has the same functoriality for G equivariant maps as the ordinary cohomology does. And the reason is it's just very simple. Since an equivariant map F from X to Y induces a map F of G from X G to YG. Okay, so that's the first fact. So the second fact is that we have a fiber bundle. So XG, this is EG cross upper G of X, goes down to BG, and this has fibers X. So this is it's taking algebraic topology. All right, this is how we write fiber bundles. This is the fiber that goes to the base. And so pull back to a fiber induces a forgetful map from H star G of X to H star X. Now this map is not necessarily surjective or anything, but in favorable cases, and maybe I should use Q coefficients here even just to be safe for part of what I'm going to say. Maybe I'll just put a Q coefficient. So as I said, it's not necessary for most of what I'm talking about, but there's a few things that might be one of these things here. So under favorable circumstances, this is surjective. So the reason is this vibration gives rise to a spectral sequence in cohomology, and this spectral sequence in cohomology will degenerate under certain favorable conditions. If that degenerates, then there'll be enough. Then this cohomology will basically look like a tensor product of this and this. So there will be enough classes here to pull back to classes here. So under favorable circumstances, this map is surjective, and so this. If, for example, so if H star ordinary X has no odd cohomology, because then this spectral sequence would automatically degenerate. Or another condition is if X is smooth and projective, That's a theorem of Deligne that this spectral sequence degenerates, and this is a vibration that would degenerate as well. So in all of the examples that we're going to be focusing on this talk, this map will be surjective. It's not surjective if x is equal to g itself, for example. So it's not necessarily surjective, but in the examples we'll be focusing it on is. So this is actually a good thing because it means that if we're interested in ordinary cohomology, we can study it using equivariant cohomology and then get it transfer information to here. Okay, I guess I should just mention one other fact, which is sort of easy, is that if g acts freely on x, so I have x goes to x mod g as a principal bundle. Then I have a fibration, which is xg, this is again, it's eg cross g of x, but now I can go down to x mod g, and the fibers will be eg, which will be contractible. And so therefore, this pullback induces an isomorphism on cohomology, and therefore h star of x mod g equals h star g of s. And with rational coefficients, this would even be true if g acted with finite stabilizers, because the fibers then would look like EG modulus some finite subgroup of a connected group which is acting. So every element of that group acts trivially on cohomology. So with Q coefficients, this is true if G acts with finite stabilizers. Okay. Now, so then the next fact I want to talk about, well, maybe it's a new topic. I should say it's a new topic. It would be Chern classes. So in this whole story, Chern classes play a tremendously important role. I want to talk about, in this setting, every representation has a Chern. So maybe before I say this, I should just so I should just say that maybe fact 4, I guess, is that there's always a map x pi from x to a point. So there's always a map from the equivariant cohomology of a point to the equivariant cohomology of x. And so in this talk, I'm gonna denote this by just h star lower g. So this is just the analogy of saying that if we're in the non-equivariant setting, this would be z or q going to the homology. But what this says, this actually turns out to be tremendously important, because this implies that h star g of x is an h star g module. And we'll see that in the case of main interest test, this is going to be a polynomial ring. So this cohomology will be a module over a polynomial ring, not just over a field or over the integers. And that's going to be very powerful. But this should be thought of as the ground ring for our equivariant cohomology. And all maps, for example, every map that we have will induce a pullback that is linear with respect to this map. So if I have f star from h star g of say x to h star g of y, a map like this will be linear for this module structure. So this is a okay. Okay, so now I want to talk about Chern classes of representations. And this is again, it's very simple. So let's let G be a representation of G. So just a complex linear representation. So then there's a vector bundle. There's a vector bundle VG on, this is just EG cross G and V on BG here. And so this vector bundle induces, this vector bundle has Chern classes. And this is going to be an H star of BG. Because every vector, if you have a vector bundle in a space, you get cohomology classes. Actually, it's in degree 2I here. And so this we will denote just by CIG of V, and that's in H star H2I G, the point. Okay, and that's the Chern class of this representation. Now, if V splits up, I'll just say C of one, I mean, I'll just say L1 plus Ln, and Xi, or I say Xk, is equal to C1 of Lk in H2, C1G of Lk in H2G, right? So if I have a splitting of my representation into one-dimensional representations, L is means line here, into one-dimensional representations, and Xk is the first Chern class of that representation, then Cig of V is just the ith elementary symmetric polynomial in X1, Xn. That's a standard fact about Chern classes. Okay. Okay, so are there any questions at this point? Okay, so now I want to move to the main protagonist of our talk, which is the torus. So I want to let T be C star cross C star with n copies here. Okay. So every irreducible representation of T is one-dimensional. And so I'll denote by T hat the set of it is these one-dimensional representations. It's hom of T to C star, and the element, this is the character group. This is isomorphic to Zn, but I want to think of this as having a basis, Zx1 plus Zxn. And here, Xi is in T hat, and in this notation, which is Xi evaluated at T1 up to Tn is just Ti. So it's just like the ith coordinate function. However, the operation here of addition corresponds to multiplication on the character side. So for example, Xi plus Xj of T1 up to Tn is equal to Ti times Tj. So it's graded additively on this side as well. Okay. So I didn't need to erase this. Oh, so if lambda is in T hat, then we get a map. So let's let T lambda be the corresponding one-dimensional representation. And so we get a map. So we have a map from T hat to H2 of T, taking lambda goes to C1 T of C lambda, that one-dimensional representation. And so this extends to a map from the polynomial ring. So if I take the symmetric algebra, I'll just tensor with Q here for now. So in this example here, this is just the polynomial ring of X1 up to Xn. That's all. That's just fancy notation for this polynomial ring. This extends to a map of here into the equivariant cohomology of a point, because each of these xi's is in H2, so I just multiply them. It's just by making it multiplicative. Okay. And then the key fact is that this map is an isomorphism. Okay, so let me say why that's true. So the proof is just the following. So I'm going to let E, G, so I'm going to decorate this with M. This M has no actual numerical meaning, but it just means that it doesn't mean, it has some slight numerical meaning. It's going to be Cm minus the origin, but I'm not keeping too close track of these homology groups. But this, I want to take this to be my space with T acting with all weights. Now I want to say Tx with all weights minus 1, but minus 1 isn't the character. My character is expanded by x, so it's going to act by weight minus x, because I have to acting with weights, all weights equal to minus x. So minus x of the character of T, T is just Tn. I guess I should have said, I'm sorry, I forgot to say this at the start. I'm going to assume here in this proof that the dimension of T is 1. Just because it's, then I can get it by like the Kuhn formula if I like. So I'm going to just say the dimension of T is 1. Equals 1, and so H star T is Q of X. And then this character here minus, the character minus X evaluated at T is T inverse. It's just what I mean by T acting with weights minus X. So then BGM is equal to just the projective space of M minus 1. And so the map Q of X going to H star of BGM is H star of PM minus 1 takes X here, goes to, well, the first Chern class of the line bundle C minus X T. And this line bundle here is actually a line bundle on projective space. Now there's only 2 line bundles it could be, either O of 1 or O of minus 1, and it's actually O of 1. So this is C1 of O of 1. And so let's just call this zeta for the moment. And so we know that, so this cohomology here of Pm minus 1, it's Q adjoin zeta mod zeta to the m. So now as m gets, for any particular I, n is going to be larger than I, or as large as I want. So this relation will not affect any particular power of x. In other words, as m goes to infinity, this relation goes away. It doesn't hit any particular x. So just to say this, as m goes to infinity, the relation goes away. And so we get that Q of x is isomorphic to H star T. Okay, so that's why that's true. Okay. Okay, are there any? Okay. All right, well, now let's, having done a point, maybe we'll actually compute the cohomology of the next. Maybe projective space. So and we're back to the case of T being, T is not necessarily one-dimensional now. I want to compute the, say Tx on a representation V with weights. Alpha 1, alpha m, and T. So let's let x equal to be equal to P and V. And I want to compute E star T of X. Okay. Well, again, so in this case, I just have to go back to my space here. So let's just say I have BT. I'm not going to use an approximation here at the moment. I'm just going to we could put an approximation. Let's not do that now. We have BT here, and we have the vector bundle VT, and we have P of VT. This is the bundle that we're trying to compute. P of VT is actually equal to P of VT, if we like. And so we're trying. So what we have to do is we have to compute H star of P of VT. Now there's a general fact about this is a projective bundle, and this general fact about the cohomology of the projective bundles is the following. So if you have, well, I'll just write it down in this example. So what this is, there's a class H and H2 of P of V. This is called the hyperplane class, and this is the class of a certain bundle. There's a bundle like O of 1, O of PV of 1. So there's a bundle on this space which is like the O of 1 bundle on any regular projective space, but just put over every fiber. And H is C1 of this class. And then the cohomology of this, it's going to be the cohomology of the base adjoined H. So it's generated by H over, and then there's a relation. And the relation is, so I learned that this is actually Grothendieck's way of defining Chern classes, which were defined in a much more complicated way before then. This relation involves the Chern classes. So it's H to the M, it's my M-dimensional vector bundle, plus, we call this map rho, plus rho star C1 of VT, H to the n minus 1 plus rho star of C m of VT. Okay. Usually I would just suppress these rho stars. I'm putting the rho stars to indicate that they're pulled back from the base, but usually, to be honest, I would just omit the rho stars and just view these classes as automatically being pulled up here. Now, the thing is that these classes here are from my module structure. So each Ci of Vt, it's Ci T of V. And this is the ith elementary symmetric function. Well, this splits up, V is equal to C of alpha 1 plus C of alpha m. So Ci T of V, it's the ith elementary symmetric polynomial in alpha 1 up to alpha m. This is just EI of alpha 1 up to alpha m. So we can write the relation here. If I suppress the rho stars, this is H to the n plus E1 of alpha 1 alpha to the m minus m H to the m minus 1 plus EM to alpha 1 to alpha m, which of course just factors as H plus alpha 1 up to H plus alpha m. So I conclude that H star T of P of V is equal to H star of T adjoin one variable H modulo relation H plus alpha 1 as a H plus alpha n. Okay, and see the reason, so these H, again, this alpha I is really a class on the point, but I'm pulling it back to P of V. Every class on the point automatically pulls back to P of V, and so we just we don't write that down. Okay. Okay, well, even though this talk is going to focus on tori, I feel like we should do at least one other group. So first we'll do the general linear group. Okay, so I'm going to let G be equal to GLN. And so I want to compute, I just want to actually compute H star G of a point. So what I want to do is I have to find a suitable space E here. So I'm going to let E, maybe I'll just call it EM for them. I'm going to call it EP. This index P is, again, it's just because of the dimension of it. It's going to be my model. I'll call it EGP. And this will be the space of P by N matrices of rank N. And I think of P as B, at least N. So this is sitting inside the space of the matrices P by N of C. This is just a vector space with a G action. It's just a representation of G. And the complement, this is open. And the complement has codimension, I believe, P minus N plus 1. So what this means is if I let P large, that complement has very high codimension, and that means all the cohomology groups will vanish up to some point. So G acts freely. Let me just call this EP for the moment. On EP and EP mod G is just the Grassmannian of, say, n planes in P space. Now, so there's something to observe here, which is useful. Is it sitting inside here, actually, in GLN contains, G is GLN, this contains T, which is the diagonal matrices. And it also has the Weil group, which is the normalizer in G of T mod T. But what we think of this is the symmetric group. And we think of this as just corresponding to the permutation matrices in G. So T again this is just C star to the N. Now this space EP, if G acts on it freely, T certainly acts on it freely. So I can use this space as a model of ET as well. And so what I get is, so I can EP as a model for BT. And so what I get is that for ET. And so I get EP mod P mapping onto EP mod G. This is going to correspond to a map of H star of G going up into H star of T. So this is a general phenomenon about subgroups, or in general even homomorphisms of groups. If I have a subgroup, I get a map in the reverse direction on the equivariant cohomology, not just of a point, but of any space. So this space here is just, it's just Q of C1, this X1 up to X. Now, what is H star G? Well, the cohomology, well, so the Grassmannian, well, it has a trivial bundle here, and then DP, and then sitting inside this, there's a subbundle S. this tautological subbundle over any point here. S is the plane that corresponds to that point. So this is the tautological vector bundle. So let's let Ci be to the ith Chern class of this bundle S, and then I'm just thinking whether there may be some. Well, this actually doesn't make any difference what I'm talking about, but so let's Ci be Ci of S. So then H star of the Grassmannian of n in P, it's equal to Q of C1 up to Cn modulo some relations. The relations all occur in degrees at P minus n plus 1. So what this means, as P goes to infinity, these relations go away as usual. And so this tells us that, so as P goes to infinity, the relations go away. And so we conclude that H star G is just Q of C1 to C. Okay. The reason I was pausing is because I was wondering whether I should not have put the dual tautological bundle here, which is possible. It's possible that should be, it doesn't, the reason is because my X's on P1 are positive, and this is sort of negative. So maybe I should put.
You haven't written down the map.
I haven't written down the map.
So you're still-
Yeah, maybe I'm still good. Okay, well, anyway, if we need to put a star, I'll just apologize in advance. So the point here is that on this bundle, we have this bundle here. We have the bundle S over to here. This is my bundle S over EP mod G. And here what I get, if I call this map, let's call this rho again for being unimaginative, I'm going to get my bundle rho star of S. And that's that's pulling back, and that's going to be a bundle on EP mod T. Now the thing is that this bundle does not split into a direct sum of line bundles. But when I pull it up here, it splits into a direct sum of line bundles. And the line bundles it splits into, if I may need to put a dual in, maybe not, is I can probably arrange it so that I don't need to put in a dual if I may have to fix my actions on my vector spaces to be correct. So, but in any event, again, it really doesn't matter. This splits into C of x1 t plus C of xn t. That bundle splits into a direct sum of line bundles. And equals here. So what this says is that C high here, this map here takes Ci to the ith Chern class of the bundle rho star of S. But this rho star of S is a direct sum of line bundles, and this is the ith elementary symmetric polynomial in the first Chern classes of those, which is x1 up to xn. So this map here, it just takes Ci to the ith elementary symmetric polynomial. So the conclusion is that H star G to H star P is injective with image. The image is the symmetric polynomials, because those are the ones that are generated by the elementary symmetric function. So the image is the W invariant polynomials, which is the symmetric polynomials.
This is true with integrally.
In this case, it's true integrally. I think if you're doing it for other reductive groups, you might need to do it rationally.
What would go wrong?
You don't get it, well, what happens is that, like, even for like PGL, you might get only O of 2 and not O of 1, so you get like 2x instead of x. So I think, you might get like, I think in the image here, maybe I won't say. I think what happens is that you don't necessarily get quite enough generators for the interval cohomology that way.
So the injective image is contained in the W variant.
It's contained in the W variance.
So it's torsion free.
No, I don't know that it's always torsion free even.
We check this in optimal stasis. This is not torsion.
I thought that was a slightly different question,
Second question.
because he was looking at the covariant ring.
Okay.
I'm not sure that it is torsion free though, actually, but in any event, I think I know that certainly Bert is studying Chow rings of these things, which he actually was very interested in the torsion and the Chow rings of these things. So certainly if you do Chow rings, these things can have torsion. And I don't so that's why I just for safety reasons I wanted to put it in print Q to avoid being forced to answer questions like that, which I would be unable to. So okay. So now I want to before doing our next big example is I want to do the equivariant cohomology, the flag variety. But before doing that, I want to talk about maybe a couple of other things really quickly. So I want to talk about well, maybe actually, just looking at the time, maybe I will do the flag variety first, because then that might take all the time. The next time I want to talk about homology and Chow, but maybe I'll save that for next time, because I think I might, if I start the flag variety now, I may be able to sort of get through it. Whereas if I do the homology first, then I may be able to get through the flag variety. Okay. So the next thing I want to talk about then is the following example. So again, G is GLN. Now sitting inside here, I'm going to let B be equal to the lower triangular matrices. And I'm going to let T be the diagonal. And again, the Weil group as before. W is Sn as before. And so I'm going to let X be equal to G mod B. And that's the variety of complete flags. So if you like, it's just 0, it can contain B 0. And I want to compute H star T of X. Now you might ask, first of all, the natural question is, why don't I try and compute H star G of X? Because the group G is acting, not just T. It turns out that for some strange reason, the group G is a little bit too big in the sense that there are no fixed points or anything. Somehow G moves everything around too much, and it's not as interesting. And it's not, in a sense, and it's also not the subvarieties that we're going to consider. There are no invariant subvarieties under the group G, whereas we might be interested in things like Schubert varieties, which are invariant under T. So so strangely, we're not going to consider the G equivariant cohomology. We're going to consider the T equivariant cohomology. Now, so just to save some writing, I'm going to let R be equal to H star of T, which is going to be Q of X1 up to Xn. Okay. Now there are two maps from T hat to H2 T of X. And then these two maps will give two maps from R. R is just the symmetric algebra into H to H star T of X. So we have two maps from R into H star of T of X. So the first map is just the first map from R. I'll just say the first map from R into H star T of X. It's just the pullback from a point. It's just the H star T module structure. It is just the But just to sort of write it down in a way that we could see it. So in other words, xi goes to the first Chern class of the bundle, the first equivariant Chern class of the bundle, x cross c xi. So cxi is a one-dimensional representation. And this is, so I guess I should have said, if you have an equivariant vector bundle, you get Chern classes in equivariant cohomology as well. Just that's kind of the general philosophy. I was saying that it has the same functoriality as ordinary cohomology for equivariant things. So vector bundle, Chern class, equivariant vector bundle, equivariant Chern class. Okay, so but this is actually a trivial bundle, but the T action is not trivial. But T is acting non-trivially on the second factor. So if we're equivariantly trivial, there'll be no T action on this factor. The second map, I'll go over here. So the second map, so given say some xi, I can define a line bundle. Maybe I'll just call it M of xi. And this is going to be a line bundle on x, which is G mod. It's going to be this line bundle G mod cross B of C of xi. And that's a line bundle over x, which is G mod B. So again, this is the mixing construction that I described before. B is this subgroup. It's acting on G on the right and on this space on the left. And the way B acts, I should just say, if B is equal to T times something that looks like this, say if B is equal to TU, well, xi is only technically a representation of T. I'm going to make it a representation of B just by defining xi of T is equal to xi. Xi of B is defined to be xi of T. So I extend that representation to a representation of B, and then I just make it here. And so this gives me C1 of M of xi in H2T. Okay. So I have so putting these together, I have two maps. I have two maps from R into this ring. So I have a map R tensor R into H star T of X. And I can think of this if I like. So again, this is the first map on the first factor, the second map on the second factor. I can think of this if I like, if I write xi, just a D's notation, right? Xi is equal to xi tensor 1 and yi equals 1 tensor yi. I can think of this ring here as just the ring in two sets of variables, y1 up to yn. So I have that map there. Now in this map, it turns out that under this map, I'll just leave some space there. So under this map, EI of x1 and xn and EI of y1 up to yn have the same image. The reason is because the reason is that the trivial bundle X cross Cn, this is it's a trivial but not equivariantly trivial bundle. It's not equivariantly trivial because T is acting here. This bundle has two filtrations by subbundles, and so I'll say it has, well, on the one hand, it's just X plus C of X1, X cross x1 plus c of xn. So it has Chern classes. So the ith Chern class is ei of x1 up to xn. On the other hand, this bundle has a filtration by the tautological bundles over the flag variety. So on the other hand, it has the bundle x cross cn has a filtration by tautological bundles, say v1 contained in v2 contained in vn, which is x cross cn, where the first term class of vi mod vi minus 1, it's the first term class of this m of xi, that bundle there that I wrote down over there, which corresponds to yi under this map. Y maps to that under this map. So the overall, so if I have a filtration, the Chern class behaves in the same way with respect to a filtration. Yes.
Like when you write C1, is it T?
Yes, it's T. It's T. Yes. Thank you. And this should be T signature. And so this first equivariant Chern class of this is yi. So that means that Ci T of this bundle x cross Cn is also ei of y1 up to yn. And so because these are different ways of representing the Chern classes of the same bundle, they're equal. And so this map factors through through q of x1, xn, y1, yn modulo the relations ei of x. I'll just say ei of x is ei of y, by which I mean those yns there. So that factors through this and this map here is actually an isomorphism. And we can write this a bit more intrinsically. This ring here, it's R tensor R. This relation here means that we're tensoring over the ring of invariant polynomials. Now it's actually it's not completely trivial that this map is actually an isomorphism. It's surjective because of a theorem which I guess goes back to Borel, which is that these classes here generate the cohomology of the flag variety. So they generate the cohomology of the fibers over the base. So these things, so I think it's surjective by this theorem maybe of Borel. It could probably, for GLN, it could be proved from a projective bundle theorem. And it's injective then because both of these modules can be seen to be free modules of the same rank. So it's not completely trivial that those two things are the same, but it is, but at least this is what the map is. Okay. So any questions? Okay, so in the last 2 minutes, I'll say a bit about homology. So when I was a postdoc, I was sort of fell under the influence, as did many people here, of Bill Fulton, and I learned, that homology is not really the same as cohomology for singular varieties, and so for smooth varieties, we have Poincare duality, but for singular varieties, we don't. And so maybe we want to have a theory that works. If we want to have a theory that works for singular varieties, maybe we should have a theory of homology. So at least that's my motivation here. So in any event, so I want to let so given x, I want to let hi of x. This is going to always denote Borel-Moore homology for us. And so this is to be thought of as the set of homology with infinite chains that are locally finite, but they're allowed to be infinite. So if x is compact, hi of x is just equal to the ordinary singular homology of x. But if x is not compact, they're different. However, the nice thing about this is that any subvariety, any closed k-dimensional subvariety y of x has a class, defines a class y in H2k of x. Actually, it's also in H2k of y mapping into H2k of x. This is a little ambiguous because sometimes you have to be, you're not sure which homology group you're considering it in. So that's a bit of a problem. But, so in any event, and this it's very similar to the Chow groups, which are because of this, it's related to the Chow groups, which are defined by algebraic cycles. So AI of x is the ith Chow group. And it's generated by classes y and of dimension. And in fact, there's a map of AI of x into H2I of x, which just takes y to y. So for our purposes, these groups are pretty similar. So I want to define HI G of x and AI G of x. And so what I want to do, so this is actually done as follows. I need to choose the appropriate model of EG. Now, it turns out Totaro was interested in studying the Chow rings of classifying spaces. And he realized that because of the functorial property of Chow groups, that if you have a vector bundle, the Chow groups of the total space of a vector bundle are the same as the Chow groups of the base space. Even though Chow groups don't really satisfy a good homotopy property, they satisfy that property. And representations give vector bundles on classifying spaces. So in any event, he realized that a good model for EG is to take an open set in a representation. So, and then it turns out, well, if you're doing this for BG, which is a point, well, you may as well just do this for any X and get equivariant Chow groups as well, or Borel-Moore homology groups. So what I'm going to say is let's let U contained in V be, so V is a representation, U is open, GX really, and U, I have a principal bundle U to U mod G. And so this is my model for EG, and so I want to define AI G of X to be equal to well, because this is homology, I have to shift dimension a little bit. So it's going to be AI plus the dimension of U mod G here of U cross GX. And then HI G of X is going to be HI plus, well, I double dimensions on this side, so it's 2 dimension of U mod G of U cross G of X. Now, one thing that's, I'm going to stop in 1 minute, but one thing that's a little mysterious is why is the dimension shift here? And the dimension shift is if you think about it, there's some choice of things of dimensions that you might put there. But one thing that you get for the, so let me say 2 last things and I'll stop. So here, the codimension of V minus U has to be bigger than the dimension of X minus I. So you have to choose something where the codimension is very large. Actually, you see in all of the examples that we were using our models for EG were this kind of model. So we actually already did this. So the only thing is I will just say the last thing is that if So in the non-equivariant case, if X is, well, there's always a cat product now. Cat product of X from HI of X to H of 2n minus I of X. This is always true for an n-dimensional variety X. And this is an isomorphism if X is smooth. Well, the relevant dimension here is the dimension of X. That n is the dimension of X. The dimension of the space that we're dealing with here is the dimension of X plus the dimension of U mod G. So we have to, so if we want Poincare duality to hold with the same degree indexing, we have to add the dimension here into the numbers. And so anyway, if I've got my dimension conventions correct, because this space has the appropriate higher dimension, if in the equivariant case, we have a fundamental class X upper G, and that will be an isomorphism from HIG of X to H2n minus I G of X if X is smooth. Okay, so that's sort of the reason for putting in this strange indexing shift in this. At least it's one reason for putting it in. Okay, so I'm over time, so thank you.
Questions?
Yes.
Why is there an SI action on the cohomology of the Flag variety?
Well, you can think of the Flag variety as isomorphic to G mod T, and the Weil group acts by the right on G mod T, because the Weil group normalizes T. So the pullback from G mod T to G mod B induces an isomorphism on cohomology.
It's also a left action.
There's also an unequivariant cohomology.
The way you explain the two sides.
But there's with the two sides, yes.
How are you choosing U and V over there?
U is an open set in a representation such that GX freely on U, and the codimension of U minus U is large.
Yes, I mean, how do we?
Well, we just chose it for GLN, and then any subgroup of GLN, you could use the same thing.
How do we do that for GLN?
We take the matrices of, so we took the space of, I call it EP, it's the space of matrices of P by N matrices of rank N, where P is bigger than N, and then the codimension, I think, is P minus N plus 1. So I can get that to be as large as I want by pushing to be large. GX freely on that by multiple computation.
Then you check that it doesn't matter which one you choose.
You check that it doesn't matter which one you choose. So basically, the way you would check that it doesn't matter which one you choose is you kind of take the product. If you take the product of two things, you can compare each of sort of factors to the product. There's a pullback. There's a projection from the product to each factor in each of that product. Those projections induce the isomorphism in the correct degrees in cohomology. Yes.
The right, should we think about G as being reductive? Is that the right?
Yes, we should think about G as being reductive. That's right.
Also different characteristic.
For the Chow groups, you can define them in other characteristics of it. That's right. That would work arbitrary characteristics. Because the Grassmannian is defined in arbitrary characteristics. So this.
Any other questions? Okay. Otherwise, let's thank the speaker.